Hello, welcome back to my channel, and in this video we are going to learn about when is a system quantum mechanical or when we consider system classical. Very roughly speaking, quantum mechanics is relevant when the de Broglie wavelength of the particle in question is greater than the characteristic size of the system. So which mean like if the characteristic size is less than the de Broglie wavelength, you cannot define his position or something like it's spread out. You can't, it's not localized. That's what it means. So when the de Broglie wavelength is greater than the characteristic size of the system, the quantum mechanical effect become very important. So let's see in some of the system when some system become quantum and when we consider them classical. So one thing to learn about, so in thermal equilibrium at temperature T, the average kinetic energy of particle of this, and then instead of P, you can substitute the de Broglie wavelength formula we learned, and then you can get this de Broglie wavelength which is dependent on this temperature. So for this problem, we wanna understand which system we consider quantum mechanical and which can be described safely, and this is from Griffin book. Okay, so you have this first let's think about solid. In the solid, the characteristic length is this lattice spacing, which is in this case is 0.3 nanometer, and we want to find the bound on this temperature where the electrons in a solid are quantum mechanical, and below what temperature the nuclei in the solid are quantum mechanical. And for nuclei we're going to use silicon as an example. So here the characteristic length is this lattice spacing d. We learned this de Broglie wavelength h over this square root of 3m kbt should be greater than this lattice spacing, which is the characteristic size, and then you can simplify it to get the temperature on one side too, because we want to find the bound on the temperature. And now we know the mass of the electron, and we can plug things. We know everything. We know Planck constant, we know mass of the electron, and we know what this kb is, Boltzmann constant, and we know the distance, the lattice spacing d, and then you can calculate the temperature, and this temperature should be less than 1.3 10 to the power 5 Kelvin, which is very large, so that's why this electron behave quantum mechanical at higher temperature, and that's why you find all these notion of quantum mechanics. So electron behave quantum mechanically at higher temperature. And then if you plug in the for sodium nuclei, here you have all these mass you can calculate because it has 23 protons and all those things. You can do that, and when you plug all the things in here, you will find out the temperature is 3 Kelvin, which is very low. So nuclei behave quantum mechanical at very low temperature. So at like room temperature greater than this 3 Kelvin, your nuclei would behave more like classical, and you can treat them classically without treat them classically without having any quantum mechanical effects in them. But when you go below 3 Kelvin, you start having quantum mechanical effect, and they will produce some observable effect, and you need to take those into account. So now let's do gases. So we want to find out what temperature the atoms in the ideal gas of the pressure quantum mechanical. Here we're going to use this PV is equal to n kBt. To this we want to find the atomic spacing. The volume occupied by one molecule is the, let's say for n is equal to 1, v is equal to d cube. We are considering like we want to find the interatomic spacing, so this volume is d cube, and you can find the d cube, the d, from using the ideal gas law, and you find the interatomic spacing. Now you know the deal as we did before. You can find that you can equate this to this characteristic, this de Broglie wavelength, and you can simplify the expression. You need to simplify a little more because there are temperature on two sides, so you need to get the temperature alone on one side and everything else on the other side, and that become inequality. And that you can do some algebra, and that's on you. You need to practice that if you are struggling with algebra. And now you can start plugging things in. For like helium, you have this mass is equal to 4 times the mass of proton at 1 atmosphere, let's say 1 atmosphere. So helium will become quantum mechanical at 0.2 Kelvin. So helium become quantum mechanical at very low temperature. And then if you do hydrogen, you have you found this D and all those things, and you found this temperature, and that is very low, and so hydrogen will become quantum mechanical at very low temperature, like 10 to the power -14 is a lot. Most of the system are becoming quantum mechanical at very low temperature. So I hope you like this video. If you do, give the thumbs up, and I will see you next time. So this is probably the end of our first fail of this quantum mechanical. Let's see how was the response, and if I wanna make more videos on quantum mechanical, I don't know. I don't know if I get if I feel like this is going good according to my expectation, which is very low. I will try to make more videos. If not, we will find something else to make. And I hope you're liking this video. If you do, give the thumbs up, subscribe, like, and share. And I will see you next time.